The if we look at the chemical shifts associated with the different carbons, what we will see is that they kind of match the protons. So if we look at the proton spectrum up here, what we see is that your aldehydes are pretty high, around 10. You have your aromatic region, your alkene region. You have your oxygens bonded to carbons, and you have your alkanes. In your carbon NMR, the scale is different. Because we have a different frequency necessary to resonate those protons. But we still see the same type of thing. Alkanes are down here, somewhere between 0 and 40. When we put nitrogens or oxygens or halogens, we tend to de-shield them, so they're somewhere in the area of about 40 to 90. Your alkenes and alkanes fall somewhere within the range of 110 to 160, 165. Then your carbonyls, which isn't showing up very well here, but what you do is your carbonyls tend to show up in this region. Ketones and aldehydes are usually around 200. Esters, amides, acids usually around 160 to 180. So there's a whole range and a whole table that we can utilize when we're looking at chemical shift. Our next NMR lecture is going to involve a new NMR experiment that we haven't covered yet, which is carbon-13 NMR. Now, the theory behind carbon-13 is the same as proton NMR. The major difference being that you only have about 1% of C13 naturally when you compare it to C12. So it is far less sensitive than proton NMR. But we still have the same principle where you have an external magnetic field and you have a carbon atom with a nuclear spin in the alpha state, and that if you hit it with a radio frequency which matches the energy, you can actually flip that spin so it's opposite of the magnetic field. And then what you do is you wait and you measure the rate of decay, or we call it a decay, going from the beta state back to the alpha state. All right, and that tends to be what the actual measurement is that we're making. It's the relaxation or the decay of that. And so what you have is you have your high energy state, which then decays back to the ground state. And what you can do is you can do a Fourier transformation on this, which is a mathematical function, and it deconvolutes this, and what you end up getting is a spectrum with the peaks on it. And again, what we do is we irradiate all the protons with all frequencies at once, and then the Fourier transformation allows us to do that mathematical transformation all at once. There are some other notes that I'd like to make before we start looking at some carbon-13 spectrum. And one is that the magnet strength is different for carbon NMR than proton NMR, and that should make sense because we talked before about the gyromagnetic ratio and that it was a constant specific for each nuclei. Well, obviously C13 is going to be different than proton, so you always just have to be aware that you often do not have megahertz in the range of things like 300 or 400. Usually they're a much lower strength. So a 300 megahertz NMR actually corresponds to 75 megahertz for the carbon. Another important point is that you cannot integrate C13 NMR. Unlike proton NMR, carbon-13 nuclei actually relax at different rates depending on the number of hydrogens they have. So it's not just about the nature, the electronic nature of the carbon, it's actually how many hydrogens. So what we find is things that have no hydrogens relax very, very slow, whereas carbons with 3 hydrogens relax very fast, and then the other 2 are in between. So the intensity of the peak actually has several things that it's related to. Also, splitting. We talk about hydrogens being adjacent to each other, splitting in proton NMR. Carbons being next to each other can split, but if you think about it, you have 1% abundance of C13, so the probability that you'd have 2 C13s next to each other is about 0.01%. Therefore, we can basically eliminate or ignore that possibility. So C13s do not split each other. So here is a typical C13 NMR. And if we look at this, I'm going to try and blow it up a little bit. All right. What you have here is based on our chemical shift that we talked about before. We've got 1, 2, 3 carbons. All right, and we have the proton NMR down here. And so we only have 2 hydrogens, and so we'll get two different types of hydrogens, so we'll get 2 signals. And then if you look up top, we have the carbon NMR. We should have 3 signals. Again, we have TMS as our standard, coming out at 0 ppm. Now the methyl proton, or the methyl carbon, is going to be the most upfield because it's only bonded to a carbon and 3 hydrogens, so it comes out here. The carbon here is bonded to 1 chlorine and another carbon over here along with the 2 hydrogens, so that comes out up here. Then finally, this carbon here is bonded to 2 other carbons as well as 2 chlorines. So since it has the most electron withdrawing groups on it, and since it's also a carbon with no hydrogens, it shows up a little more downfield, so we're around 90 ppm. So that is, again, very similar. We really only have to focus on chemical shift when we're dealing with carbon NMR. So we take another example, and we are going to look at this molecule right here. And so we know we have 1, 2, 3, 4, 5 different protons. It turns out that some of these are going to be located underneath each other, but we have 5 different protons. We have the aldehyde coming out way downfield around 9.5. And then we have our 3 hydrogens here coming out in the aromatic region, and they're showing up here. Okay? And it turns out that our NH, we talked about that being exchangeable, it actually doesn't show up in our NMR. So that's the reason why we don't have that 5th proton there. But now what I'd like to do is I'd like to expand that and look at the carbon NMR. All right, so here we go. And if we look, we have our 3 protons, our 3 carbons, actually 4 carbons now of our aromatic ring should show up in the aromatic region. And there they are, 4 carbons in the aromatic region. And then our aldehyde carbon is going to show up downfield around 180. You'll also note you'll very often see a triplet around 77. So a triplet around 77 ppm is associated with the CdCl3 solvent because it does contain a carbon. And it turns out that it couples to deuterium, so that's why you see a triplet. You don't have to understand why. What that does lead us to is another topic, which is we said that carbons will not couple to each other because there's not enough of them. But what about the carbon that's directly bonded to a hydrogen? Hydrogens are NMR active. Carbons are NMR active. So carbon and hydrogen can couple to each other. And you use the same rule. We use the N+1 rule. So let's say we take, for example, this molecule here. And we look at the CH2. It's 2 hydrogens directly connected to the carbon. Therefore, if we did our N+1 rule, we'd expect a triplet, which is what we see. The CH3 bonds to 3 hydrogens. N+1, we'd expect a quartet. Notice the carbon in the middle here has no hydrogens which are bonded to it. N+1 would be a singlet, and that's what we see. So you can get proton-carbon coupling. However, you tend to get very complicated NMR if you leave splitting on. And so what happens is we actually decouple the proton and C13 signals coupling, and therefore what you get is only singlets. So you will only see singlets in the carbon, and there you can see the difference. The coupled NMR on top, when we decouple it, which we can do, we simplify the spectrum and it becomes very much easier to read. And here we go, more complicated NMR. We look at it. We'll go over this in class, but here we got 1, 2, 3, 4, 5, 6, 7 signals, again, because these 2 are equivalent. They're chemically equivalent carbons. And we have 1, 2, 3, 4, 5, 6, 7 signals in the carbon NMR. However, when we do decouple, we lose information because we lose how many hydrogens are on a particular carbon. Well, we can gain that back by doing another NMR experiment. And this is referred to as DEPT, all right, D-E-P-T. I believe that stands for Distortion Enhanced Polarization Transfer. You don't have to worry about what it means. But basically what I want you to focus on is this. And when you run your DEPT experiment, it's going to look like a carbon. But it will be different because any quaternary carbon, any carbon that doesn't have any hydrogens on it, such as the one drawn, or a ketone, ester, even let's say an aromatic ring that has a substitution on it. So this carbon right here, those will not show up in depth 135. A CH will show up, and it'll show up as a signal pointing up. A methyl will show up, and will also point up. And then we get some information here. If you have a CH2, it'll actually point down. Spectrum here, if we take a carbon NMR of this compound here, which is methyl vinyl ketone, we have 4 carbons. 1, 2, 3, 4. In the depth, and again, this is C, this is what we're looking at. Carbon B there, that has no hydrogens on it, so it will not show up in the depth. Carbon A has 3 hydrogens, so it shows up and points up. Carbon C has 1 hydrogen, it will also point up. And again, you don't get any CH3s down here, so the only possibility is a CH. The D here is a CH2, so that will point down. So you're able to determine which signal in your carbon NMR actually corresponds to the CH2 of the alkene. So we gain some of that information back that we lost from decoupling our carbon when we run a depth. So that covers carbon NMR, and what we'll do from our next classes is go over problems and kind of put everything together.